In-class activity 11B, building a test statistics. Bottled water companies spend huge sums of money to market their product, touting its purity, rejuvenating minerals, and superior taste. At the same time, environmentalists are concerned about the impact of all those plastic bottles, many of which are not recycled. Why does bottled water remain so popular? Do consumers actually prefer the taste of bottled water, or are there other factors at play? 1, how would you design a study to test water consumers prefer the taste of bottled water or tap water? How would you design a study to test whether consumers prefer the taste of bottled water or tap water? Answers will vary. Answers will vary. This is a sample answer. We can set up a testing station with 2 unlabeled water sources, one containing tap water and one containing bottled water. Ask participants to try both and decide which one they prefer. Record the proportion of participants who prefer bottled water. That's one way to do it. The objective for the activity, you will understand that a test statistics can be used to assess the strength of evidence against the null hypothesis. When working with proportions, if the sample size is large enough, a normal distribution with a mean of 0 and standard deviation of 1 can be used to model the distribution of the test statistics that would occur if the null hypothesis were true. You will also be able to calculate a test statistics and interpret its value in context. Also use the test to decide whether the null hypothesis. We use the test statistics to decide whether the null hypothesis about a population proportion is a plausible explanation for sample results. 2, you conduct a test to investigate whether consumers prefer the taste of bottled water or tap water. State the null and alternative hypothesis in words. The null hypothesis is that consumers have no preference for bottled water or tap water. The alternative hypothesis is that consumers do have a preference for either bottled water or tap water. B, part B of number 2. State the null and alternative hypothesis in terms of the proportion of consumers who prefer bottled water. So the null hypothesis H0 is that P equals 0.5, that is 50%. And the alternative hypothesis would be that P is not 0.5, that is different from 50%. All right. For problem number 3, consider 4 data sets that might have resulted from the test. Which of the 2 tests below would provide more evidence of a preference for bottled water or tap water? test A, here the results show that 30 people participated, 17 preferred bottled water. Test B, 30 people participate, 21 prefer bottled water. So here, which of these two would provide more evidence of preference for bottled water or tap water? In this case, test B provided more evidence because the proportion is bigger. B is 21 out of 30. Here it is 17 out of 30. 21 is bigger than 17, so B provides more evidence. All right. Let's look at more scenarios. Which of the two tests below would provide more evidence of preference for bottled water or tap water? Test C, we have 22 out of 50. Test D, we have 44 out of 100. In this case, the proportion is the same in both cases. It's 0.44 if you find the proportion in each case. That is 22 all over 50 will give us 0.44. And of course, 44 all over 100 will still give us 0.44. So the proportion is the same, but because D involves a larger population, a larger sample, right? 100. So we choose test D. Okay. Now, which of the two tests below would provide more evidence of a preference? Is it B or D? The same B and D we have seen before. As a hint, it may be helpful to calculate the sample proportion and locate those values on the appropriate sampling distribution given the next page. But here we can see that test B provides more. B is 21 out of 30. D is 44 out of 100. 21 out of 30 is 0.7 or 70%. This one is 44%. We've seen it here. So 0.7, 0.44. 0.7 is bigger. So test B is the choice. So we can look at the explanation this way. The graph below are sampling distribution that show the proportion we would expect to choose bottled water in the sample if there were no preference in the population. When the sample size is 30, the standard error is 0.091, and we have this distribution. When the sample size is 100, the standard error is 0.05. The larger the sample size, the smaller the standard error. And a test statistics measures the distance between sample statistics and the null hypothesis value in terms of the standard error of the statistics. So as a formula, test statistics equals sample statistics minus null hypothesis value divided by standard error of the statistic. Let's look at them more closely. When the sample statistics is a proportion like it is in this example, the test statistics is also called a z-statistics. So let's calculate the test statistics for each test. So we're looking at test B and test D. B and D. In B, 21 out of 30. In D, we had 44 out of 100. We already saw this proportion before. 21 out of 30 is 0.7. 44 out of 100 is 0.44. Now, let's calculate the test statistics. This is the new part of this problem. So this is the sample proportion, 0.7 minus 0.5, which is the value from the null hypothesis, divided by the standard error. That will give us 2.198. You can put this on the calculator carefully and see that you get 2.198. When we do the same for 0.44, 0.44 minus the same 0.5 divided by the standard error now, which is 0.05. When you divide, you get negative 1.20. So we have the test statistics in each case. This one is 2.19 something. This one is negative 1.2. Part B, it says, write a sentence to interpret the test statistics for test B and test D. Well, we'll be interpreting the test statistics, these numbers we calculated. So let's see how we interpret it. We said that in test B, the proportion who preferred bottled water was 2.198 standard errors above the null hypothesis value. In D, the proportion who preferred bottled water was 1.2 standard errors below the null hypothesis value. Below because it's negative, and above here because it is positive. That's the interpretation. The number of standard errors below or above the hypothesis value, the null hypothesis value. All right, that is part B. Let's look at part C. Part C says, write a sentence to describe how the test statistics and the evidence against the null hypothesis are related to each other. You can write this in different ways, but the sample answer is this. As the test statistics gets further from zero, there is more evidence against the null hypothesis. So as the test statistics you are getting goes further and further away from zero, whether above or below, there is more evidence against the null hypothesis. Okay. Assuming the sample size is large enough, we can use the normal distribution to model the values of the sample proportion that would occur if the null hypothesis were true. In lesson 9C, we learned that the sample size is considered large enough when the following condition is met. NP is greater or equals to 10. N times 1 minus P is greater or equals to 10. N is the sample size, this is the proportion. So if you get a value of at least 10 in each case, then we say it is large enough. Since the normal distribution is being used to model the values of the sample proportion that would occur if the null hypothesis were true, we check the condition by replacing P with the value from the null hypothesis, which is 0.05 in the bottled water test. The graph below shows the null distribution for a sample size of 100, where the standard error, of course, is 0.05. Note that the mean of the null distribution is 0.5 plus the value from the null hypothesis in the bottled water test. So what values of the test that would occur if the null hypothesis were true? So we're going to use this table. It's kind of faint, but we have 0.5 in the center, 0.55 is next, 0.6, and then 0.65. And then on this side, we have 0.45, 0.40, and then 0.35. 0.35, 0.40, 0.45. In the middle is 0.5. The next one is 0.55, 0.60, then 0.65. We'll come back to this table as we look at each of the questions on problem number 5. A says, if the sample proportion were equal to the null hypothesis value, which is 0.5, the test will take a value of what? 0, because you do 0.5 minus 0.5 divided by the standard error. That will give us 0. 0.5 minus 0.5 divided by the standard error. That will give us 0, because the numerator is 0. And then if we do the same for B, if the sample proportion had a value that was one standard error above the null hypothesis value, that is 0.55, the test would take the value of what? 1. So 0.55 minus 0.5 divided by 0.05, that will give us 1. 0.55 minus 0.5 divided by the standard error, 0.05, that will give us 1. And we can also see it from the normal distribution table that we saw earlier. And we can use this idea to find, for part C, find the value of the test that is for each numerical value marked on x-axis of the normal distribution above. Write the values below the x-axis. So let's go to it. We've written the values there. So we already know that if you have 0.5, z will just be 0. And so if it is 0.55, z will be 1. So we can just label them z equals 1, z equals 2, z equals 3. And this side it will be -1, -2, -3. So we can label all of them. So we don't have to use the formula to calculate each one. The middle is 0. The next one is 1 to the right, -1 to the left, 2 to the right, -2 to the left, 3 to the right, -3 to the left. So we have all of them written next to it. Okay. So that's what we mean by saying the answers are written below the x-axis. We showed it. Let's go to number 6. The test was conducted with a group of statistics students in Florida. Out of 22 who participated, 20 preferred the taste of bottled water. Now, before you calculate anything, make predictions about the Z status. Do you think the value will be positive or negative? do you think the value will be far from 0 or close to 0? We have a total of 22, 20 of them preferred bottled water. That's very high. 20 out of 22 is almost all of them. So, of course, we can write our answers in different ways. Answers would vary. But a sample answer would say, I think the Z statistics will be positive because it's big, because more than half of the students prefer the taste of bottled water. I think the Z statistics will be far from 0 because almost all of the students preferred bottled water, which would provide evidence of preference. This would provide evidence of a preference for bottled water. That is part A. Let's look at part B. Let's look at this one at a time. When the sample size is 22, the standard error is 0.107. Why is this standard error larger than the standard error for the test B and D we saw earlier? Well, the answer is because the sample size is smaller. The smaller the sample size, the larger the standard error. Let's write that. The smaller the sample size, the larger the standard error. Because we're dividing by the sample size. So if you're dividing by something smaller, then you get the result that is bigger. If you're dividing by something huge, of course, you get something smaller. Okay. So let's calculate the test statistics for this sample. And it comes out as 3.82. Remember, to calculate it, we remove the proportion from, remove the null value from the sample proportion divided by the standard error. So let's do it here. Remember, out of 22, 20 of them picked it. So it's 20 divided by 22 minus the value from the null hypothesis, which is 0.5. Then we divide it by the standard error, which is 0.107. You can put this in parentheses. This 0.107 is the standard error. When we divide this, let's do it in the calculator. So we have 20 divided by 22 minus 0.5. That gives us 0.409090909. So you divide it by the standard error, 0.107. and we have 3.823279.524, which we can round to 3.82. Okay, so we know what the test statistics is for this sample. D, is it reasonable to use a normal distribution with a mean of 0 and standard deviation of 1 to model the distribution of the test statistics that would occur if the null hypothesis were true? Hint, check the sample size condition. We know the sample size condition we need to check to make sure we can use normal distribution. We say yes, because NP, which is 22 times 0.5 is 11, and N times 1 minus P, 22 times this is also 11. Both of these values are greater than 10. So the sample size condition is met, and therefore the normal distribution can be used as a model. The normal distribution can be used because these two conditions were satisfied. NP is greater or equals to 10, N1 minus P is greater or equals to 10. So we can use the normal distribution as a model. All right. Is the null hypothesis, that is no preference for bottled water or tap water, a plausible explanation for this data? Why or why not? Is it a plausible explanation? We know answers would vary, but in general, we say no, because if the null hypothesis were true, the Z statistics would usually take values between -3 and 3. The Z statistics of 3.823 would be very unusual. So we got 3.823 something. This is unusual because otherwise it would have been between these two. Okay. We said answers would vary, but the essential statement would be the same. So the answer will still be no. Okay. Do you think it is safe to generalize this result to other parts of the country? This result we got in Florida. Do you think it is safe to generalize these results to other parts of the country? Although answers will vary in the way we state it, but the general thing should be no, because the tap water that these students were drinking may taste different from the water elsewhere. So we cannot use this one to generalize it unless we can prove that the water in Florida that these students were drinking is exactly the same as the one other people are drinking everywhere in the country, which is not true. So the answer is no. And with that, we come to the end of this lesson 11B.